Hi, I'm Sayeeda Kutsia from Abu Academy University, and I'm going to present about determining surface recombination velocity at a blocking interface and the results we got in this regard. Titania is a very common electron transport layer in thin film solar cells, and while transporting electrons, it should also be blocking holes. This hole blocking property can be studied using CELIV. MIS-CELIV is when the technique called charge extraction by linearly increasing voltage is done on metal insulator semiconductor structures. It works by injecting charge carriers in a single carrier device, which was a hole-only device in our case. In structures such as thin film solar cells, there is going to be a built-in field due to work function differences between different layers. When an offset voltage greater than this built-in field is applied, holes are injected into the device. They accumulate by the blocking layer, but some of them recombine with electrons across the interface, contributing to the steady-state dark current, JD, going through the device. In CELIV, a linearly increasing voltage pulse is then applied in the reverse bias to extract these charge carriers. This results in a transient, with the capacitive response of the device J0 and some delta J that refers to the extracted charge. By taking into account the extracted charge and the steady-state dark current, surface recombination velocity can be calculated according to this equation. We used sol gel dip coating to make titania layers with different thicknesses, using two different substrates, ITO and FTO, FTO being much rougher compared to ITO. We then processed these layers into devices for MIS-CELIV measurements. We found that the surface recombination velocity decreases with increasing titania thickness. This is due to better hole blocking of the titania layers, likely due to better surface coverage that is offered by the thicker layers. If the layers are otherwise defective, we again see that the surface recombination velocity increases. As we see for our 84 nanometer titania layer, where due to low density, the layer tends to disintegrate and forms cracks. Hence, it is important to ensure substrate coverage to reduce surface recombination in functional devices, and MIS-CELIV is a good technique to study such properties. Further, we tried visualizing the conductive substrates using conductive AFM. Here, ITO and FTO have been covered with a very thin titania layer. As FTO is much rougher, the titania layer tends to fill in the valleys in the substrate first, leaving the tips exposed, and we see conduction through these. Around 8% of the substrate was exposed in the case of FTO, compared to less than 0.13% for the smoother substrate. So either the layer should be thick enough to ensure substrate coverage, or a smoother substrate can be used that is easier to cover. We would like to thank Jane and Atos Erkko Foundation and Academy of Finland for funding. Thank you for listening.